All right, we're going to talk about waves today, starting a couple lecture segment on waves. So we introduced waves when we were talking about electromagnetic radiation as in its relevance for the greenhouse effect, but waves are a topic that are shared by many different, probably all branches of the earth sciences, and so there are aspects of waves both in terms of the natural phenomena and also the way that we interrogate different bodies, the solid Earth, or from satellites, looking at remote sensing and so forth. So waves are a general topic that's of importance for Earth systems. And so I'm going to start by doing some sort of general introduction, or continuing our introduction. There'll be a little bit of a review here. And then we'll get into some specific examples of waves that are relevant for Earth systems. So a wave is a disturbance. And by that we mean a change from equilibrium that propagates or oscillates repeatedly about a stable equilibrium. Let's say a stable equilibrium value. And an important aspect of waves is they transfer energy. So this was something that was very explicit when we were talking about electromagnetic radiation, right? Moving energy from the sun to the earth and then back from the earth out into space. But it's a characteristic of all waves. So why study waves? So there are many important subsurface, oceanic, and atmospheric processes. Many important subsurface, oceanic, and atmospheric processes are waves. So we're just trying to kind of understand how the planet works. And as I mentioned, the energy that allows for life on Earth. Life. Is transported by waves. And we also use waves to explore. So for example, remote sensing is satellite-based analyses of electromagnetic radiation. Sort of, looking at different spectra to figure out how much water is in the air, or how much photosynthesis is happening, and that sort of thing. Spectrometry helps us figure out what materials are. So now analyzing molecules and minerals. They're also important for things like radar and geophysical exploration. So we set off different make loud noises and look at how the waves travel down and bounce back, and that helps us figure out what's underground, including mineral resources and oil. Okay. Why do waves occur? So there's some disturbance, as we mentioned. We could call this a generating force that causes the disturbance. Okay, something's knocked out of equilibrium. And then there's a restoring force that wants to pull or point back towards equilibrium. So for example, if we were talking about sound waves, that restoring force would be the air pressure. So as the wave, as say your speaker pushes the air, that causes like a higher pressure in an area right next to the speaker, and the air wants to go back to a constant pressure everywhere. So that would be the restoring force, is the pressure going from areas of high pressure to low pressure. So molecules actually moving to equalize pressure, and then that sort of overcompensates and pushes some more molecules, so the pressure is higher, and on and on. So this disturbance propagates. And I'll show an example of this in a moment. Why don't I show it? Why don't I do that now? Okay. Here we go. Okay, so this is an example of what's called a compressional wave. And you can track a given particle, and you see that it just moves back and forth, right? So the particles aren't moving across the screen. It's the wave is, right? Here goes the wave across the screen. And you can sort of imagine like where the molecules are all close together, that's an area of high pressure, and where they're pulled apart, it's an area of lower pressure. So the wave is causing this oscillation in pressure. So most waves travel through the medium. So for example, in the example we were just looking at, that was air molecules. So the waves were traveling through the air in that case. The exception is electromagnetic waves. Okay, so if you're, it's one of the things about some of these movies where there's an explosion and a spaceship explodes and you hear a big explosion sound. So that wouldn't happen, right? You could see the flash of light, electromagnetic waves, but the sound requires something to travel through, some air or some material. All right. So let's go through some terminology. Okay. So amplitude is the distance from equilibrium level to top or bottom. And here we're talking about a wave that has a shape like that. So amplitude in the case of the sound wave we were just looking at, so this would be, let's call amplitude A for now. Amplitude for the sound wave is if we charted, so this might be for a water wave, the y-axis might be height, might be in meters. For a sound wave, we might plot the pressure of the air, right? So we go from like very high pressure areas to lower pressure areas. The height is 2 times the amplitude. So it's the distance from what we're going to call the crests to what we're going to call the trough. Let's call height little h for now. And we've talked about wavelength before. Lambda, the distance between successive crests. So this distance here. And notice that there's been no mention of time so far, okay? So the next terminology that we're going to give is related to time. And wave, you might be listening to this, writing these things down, thinking, yeah, I've heard this review, but it gets pretty quickly, it can get a little it seems simple, but it's easy to get tripped up because of how waves can have, be plotted in terms of like distance or in terms of time. So try to pay close attention here, and we'll have some examples. So velocity, right? That is analogous to the speed of light that we were talking about, but more generally, we're talking about velocity for waves. It's not a constant. So we talked about electromagnetic waves, and we just had this constant c, right, the speed of light. But for other waves, that we can't just assume that they're all going to travel at the same rate. Frequency. So frequency, it's the waves that pass per unit time. And the units are hertz, which is the number, another way to say this, cycles per second. And frequency is defined at a point. So we don't see, or we don't need to see the whole wave. And frequency, as we described, is it's related to both the velocity and the wavelength. Okay, so you could have the same frequency, and here's an example of this. Okay, so just sort of from the bird's perspective, just looking down at this crab kind of going up and down. So all the bird needs to see is that crab to know the frequency, right? So the same, we could have a fast velocity but a large wavelength, and that would give us the same frequency as a short wavelength and a slow velocity. So I've got an example of this as well. Okay, just a second, let it load. Okay, so I'm going to set, so this is, I can change these things. The amplitude, right, is going to make the wave, that's a larger amplitude, smaller, zero amplitude. Okay, let's make a nice big amplitude, and so take a moment and just ask yourself, okay, what is the frequency of this wave? How would you measure the frequency of this wave? Maybe pause the video or just think about it for a moment. Okay, so the frequency is the number of like crests that pass by a particular point in a moment. So we could just look at this last dot kind of going up and down, and it's going up. Maybe we could set a timer. We'd say, okay, it went 1, 2, 3, and then we'd say divide that by how much time it took. Okay, so we've set the frequency here. We could also change the wavelength, right? Okay, so here we have a smaller wavelength, but notice that this thing is going up and down at the same rate as before. So up, down, up, down, up, and even if I do this, it's still doing that, right? Up, down, down. Okay, so even despite the fact that the wave is, so in order for that to work, that's that relationship between this distance and the velocity. Okay, so if you're going to have a large wavelength like this, then the wave needs to travel really fast to maintain that same frequency. But if you have short wavelength, it can travel relatively slowly. And from the perspective of the bird sitting here and watching this crab move up and down, it can't tell the difference, right? And that's because the frequency hasn't changed. So I'll just highlight that so you can see this web address in case you want to play with it yourself. Okay, a term related to frequency is period, which we're going to use just a capital T. And the period is the time between passage of two crests. And the period is simply 1 divided by the frequency. And I should note, previously we used a different letter. We use nu for frequency, but going forward, let's use F. I think it's going to be just simpler to remember. And then we can use V for velocity and not get it confused with nu. Okay. So So just if we know the frequency, we know the period. We just divide the frequency by 1. And so since frequency had units of per second, the units of period are going to be time, right? So seconds. So let's look at this. This again. Okay, so the frequency we counted. So I'm going to get a stopwatch here. Okay, let's see if we can. Let's actually put a. All right, so it's going to go from there. Okay, down. I'm timing this. So there's 1, 2, 3, 4, 5. Okay, that was about 10 seconds. So the frequency was 5 divided by 10 seconds. So one half. So the period is 2. So what does that mean? Let's go back to the definition here. So the time between the passage of 2 crests. Okay, so if we stood here and instead of counting, looking at this thing going up and down, if we're just like, okay, 1, how long does it take until the next one? There it is. So 1, 2, might have messed this up. Let's try again. There we go. Yeah, 2 seconds. Okay. So let's look at this. Let's just say this a little bit differently. So waves can be measured with respect to time or space. So spatially, it's like an example would be looking down at the ocean from a cliff. You could see. I see waves down there, and they're space is far apart, right? Alternatively, temporally, we could. So this is tracking motion of a point. So this would be like sitting by the beach and listening to the crash of the waves. So you could get a stopwatch and be like, oh yeah, the waves, every 5 seconds the waves crash. So that would be a period of 5. And there's a diagram that's kind of useful here for thinking of this. So if this was, so let's start out with spatially. So the x-axis here would be distance. Let's do another one here so we can. Okay, x-axis is distance, and we could define, as we did before, the wavelength. We could draw a very similar graph, but instead of distance on the axis, we would have time on the axis. Okay? And in that case, what is that distance here? Or what is this? I shouldn't say distance. We're in the time, so we're in the time domain here. Here we're in space. So what are we measuring here when we measure in terms of time? So for example, this would be some number of seconds. This is the period. So period is analogous to the wavelength, and it's when we're in the temporal domain. It's worth rewriting so that we talked about last week how the motion equation is an analog for waves. So using the new symbols we're using, So we have wave velocity is, it's going to be a distance over time. So it's the wavelength over the period, right? Or that's the same as wavelength times frequency. So these are the kind of things that, like, you're probably going to want to ask yourself at a later time, okay, can I come up with these equations so I understand this? Can I draw these graphs? Let's look at an example. So the example we're going to look at is seismic waves. So the disturbance is a sudden motion of rocks, so generated by earthquakes. Which is the sudden sliding of rocks on a fault. And earthquakes generate different kinds of waves. So let's talk about this for a moment. So earlier we looked at an example where we had some particles that were close together and then more spread out, right? And then they were more together and then more spread out. So this would be called a compressional wave. So the motion of the wave, let's just say it's moving in that direction, and these particles are moving. An individual particle is moving backwards and forwards in the same direction as the wave itself is moving. But we also have waves where the particles move at a right angle to, so these are like little arrows. So we have particles, so at a given point in time the particles are doing this, right? The particles are moving, the motion of the particles is at 90 degrees to the wave direction. Wave motion, or we could just say velocity. So the velocity is going this way. So this we call a shear wave. So these could be air molecules. These could be, for earthquakes, these could be mineral grains moving back and forth. So seismic waves, the first one to talk about is called the primary wave, and that's just abbreviated P wave. These are compressional waves. And they travel through all material. And they're the fastest of the seismic waves, moving around 7 kilometers per second. So they're called primary because they get where they're going first. Unlike the secondary waves, which get there second, and are abbreviated S waves. So these are shear waves. and they don't travel through everything. They travel through solids only. And they move at a slower speed, around 3.5 kilometers per second. Okay. And the reason that they don't travel through liquids, and they wouldn't travel through air. And the reason is because there's not a restoring force for the lateral motion. Okay? So if the earthquake shears the material, so that, you know, maybe you had some atoms that were like this, and then they got, there's a liquid and they got jostled like that. Okay? So in a solid, there's a bond between these things, and elasticity wants to pull it back the way it was. For a liquid or a gas, right? These molecules are like, okay, I'm fine over here, so they just stay there. So the shear wave doesn't move. So that is a really important characteristic of seismic waves. So there's a lot you can do with just the fact that these two different waves, and looking at a seismogram. So if you're tracking with time the motion of the Earth, you know, it's like, okay, a truck drives by, and then you have an earthquake. You get this kind of like that's the primary wave arriving first, and then later on you get the secondary wave. So given that we know the speeds of the waves roughly, we can tell how far away we are from the earthquake. And there's another important thing to know about this is, let's say, so here's the Earth. Okay, so these waves and their characteristics were used to determine that the Earth has a liquid core. There's a solid core in there too. So let's say, and the reason is like let's say there's an earthquake here. Okay, so there's the waves travel, and we have both the P and S waves arrive at some places. But there are other places where the wave travels through the center of the Earth, and only the P waves arrive. So the signals that are measured at different station are very different. So they'll be up to some point like that, where you have P and S, and then you have what's called a shadow. No S waves. So this knowledge of the P and S waves was used early on to gain a fundamental understanding of the interior of the Earth. And there's other characteristics of seismic waves that are useful. For example, the velocity of the P wave divided by the velocity of the S wave. It's called VPVS. That can differ according to composition. So VP and VS, I gave some rough estimates of their velocities, but they differ. They can vary depending on the material they're moving through, and we can tell, for example, like a limestone from some granite, that kind of thing. So looking at, closely analyzing the seismic waves that are generated by earthquakes and also by man-made sounds, we can learn a lot about the interior of the Earth. And probably the most, let's say, economically relevant use of this is they're used for hydrocarbon exploration. So you set up a bunch of seismometers. So this would be the surface of the Earth. You set up seismometers to look at the motion. You set off an explosion, and the waves travel, and they end up, if there's let's say there's some rock layer that does something like that. So the waves are bouncing off of this thing, and when you collect all the data from all these places, you can see that there's a boundary down there that's curved, for example, and that would tell us, okay, yeah, there's if there's gas down here or oil, this is the place that you're going to want to drill, right? So the petroleum industry spends a lot of money doing this kind of work, figuring out what's hundreds of meters to kilometers underneath the surface, using these waves, generating their own waves. And there's one more major category of earthquake waves, surface waves. So these travel, as you might guess, travel along the ground. And they're either horizontal shearing, so that would be, let's say there's some ground, surface of the Earth. So the way the ground would kind of jostle back and forth like that, sideways, right? Or it can roll like water, like the water waves we're used to. So the ground could also go up and down like that. And surface waves are the slowest waves. They go around 2.5 kilometers per second. And they also cause the most damage. Of the three major kinds, the P, the S, and the surface waves, in terms of destroying buildings and that kind of thing. So that's just a glimpse of an example of one kind of wave. And I'm going to end this video by playing a clip, and what it is a recreation of the seismic waves generated by the Tohoku earthquake in Japan in 2011. So that was that big earthquake that where there was a tsunami associated with it that flooded over the tsunami walls and caused the Fukushima reactor to be destroyed and all that. And so the video is from the perspective of the whole Earth, and it shows a different it's a different view than we're used to looking at. And so it's sped up over time, because at these rates, right, 7 kilometers per second, it takes a while for the seismic waves to bounce around in the earth. But when these earthquakes happen, the earth basically rings like a bell. And so the other thing that the creators of the video have done is they've taken the waveforms. So the seismometer. So let's talk about that for a second. So the seismometer, basically, like the classic seismometer was a roll of paper spinning around, and it just has a pen that's just drawing a line, and it moves back and forth, right? So if you look at that, like if nothing's happening, if there's no earthquakes, the pen is just going to pretty much stay in the same place, except for how it's moving sideways. But then if there's an earthquake, it's recorded, right? It shakes. So what the creators of the video have done is they've taken this and just put this waveform into a speaker. And so in order to do that, they've also needed to speed it up as well, so that it's in I think it's a speed up. They've changed it so that it's within the frequency range that our ears can detect, because generally these are going to be lower frequencies than we would be able to hear. So they've sped it up, but it is what you're going to hear is the actual sound of the actual waveform of the earthquake. Okay, so it's going to look at both surface waves and then body waves.